Good morning. My name is Francis Yaupnyo, research scholar, Assam Don Bosco University. So the topic that I will present today is on noise-assisted particle transport and particle diffusion in an underdamped inhomogeneous periodic potential system. All systems at a finite temperature, it experience this minute random fluctuation in temperature, which are called noise or fluctuation. In the macroscopic level, these are negligible, but in the microscopic domain, these random fluctuations at times play a counterintuitively constructive role, resulting in interesting phenomena like Rorschach effect. In this work, we study Rorschach effect and particle dynamics in a model underdamped inhomogeneous periodic potential system. Rorschach effect is a phenomenon in which the particle undergo directed motion assisted by this random fluctuation without any external bias. This study of particle dynamics in this system is inspired by the possibility of controlling and fabricating nano devices which can have tremendous technological application, particularly the possibility of controlling particle current and diffusion as a function of the various parameters of the system. This is a model. The one-dimensional equation of motion is given by the Langevin equation. This is the Langevin equation uh, given by equation 1, where Ft here is the external drive. This term represents the stochastic term, and Jt here is the random fluctuation. T is the temperature in Boltzmann unit, where Jt is satisfy these statistics, and the periodic potential is given by this relation. Vx is of this form: V naught sine kx plus B sine 2kx, where B here represent or determine the asymmetry of the system. So B is called the asymmetry parameter. So if B is 0, then the potential is symmetric. And the space-dependent friction coefficient is gamma x, which is given by this relation, gamma naught 1 minus lambda sine of kx plus phi, where lambda here is called the inhomogeneity parameter. So if lambda is 0, then the system is homogeneous. And this friction coefficient, gamma x, is having the same period as the potential, but with a phase difference of phi with the potential. And the external periodic force Ft is F naught cos of omega t, where F naught is amplitude of the drive, and this drive is having an average of 0 over the period of the drive. So that means the system is not biased. This is a model that we have plotted. Here we have plotted the potential with the symmetry as well as without asymmetry, as well as the friction coefficient, where the asymmetry here we included is we put it 0.7. So this is our model that we have plotted here. And of course the phase difference between the friction coefficient and the potential is 0.35. So the equation 1, the Langevin equation, we reduce it in dimensionless form by setting m is equal to 1, k is equal to 1, and v naught is equal to 1. So therefore the reduced equation, or rather the equation in dimensionless form, is given by this relation 2. Again here, this random fluctuation Jt still satisfy the same statistic. This equation 2 cannot be solved analytically, particularly in the presence of external drive. So we are solving this equation 2 numerically using the second order Huynh method of solution of stochastic differential equation. Huynh method is nothing but is a Runge-Kutta method in the presence of stochastic term. The average velocity of the particle is obtained by this relation in the long time limit, where we allow the particle to evolve over a long time, t is to infinity, and here the averaging is averaging over ensemble averaging is xt by t, and the diffusion coefficient which measure the spread of the particle is denoted by t, which is given by this relation. Here, as what I mentioned, the particle is allowed to evolve over a long time, that is 10 power 5, and the ensemble average is done over ensemble of 50 different initial condition, because the dynamic of the system is sensitively depend on the initial condition of the system. And the Piglet number, which is a measure of coherency, which is defined as a ratio of average velocity divided by the diffusion coefficient into L, where L here is the characteristic length of the system. So Piglet number here, it measures both the spread and the velocity of the particle. Now this is the result that we have plotted. In the first, we have plotted for the three value here. In the first plot, you have see here the drive is 0.4 without tilt, without asymmetry. That means the system is not externally biased. So we see that even without any tilt, without any asymmetry, that means without any external bias, still we are obtaining a ratchet current here. Now in the second plot, we have included a small asymmetry without tilt, a small asymmetry of 0.05 for the same periodic force 0.4. And if you look here, the ratchet current we have obtained here, it increased substantially. And it is almost twice than the earlier one without asymmetry. And in the third case, we apply a small tilt along with asymmetry in the negative direction. Even though we apply a tilt in negative direction, still we are obtaining a current in the positive direction. So this shows that even with a tilt applied in negative direction, we are obtaining a ratchet current in a positive direction. That means we get a positive ratchet current. So this shows that the ratchet current, it works against the loop. And if you look here around this region, we are also obtaining a reversal current. So this is very important for particle separation technique. So we are obtaining a resonant line of ratchet current with temperature. So even though the ratchet current increases substantially with the include of asymmetry, but diffusion is almost remain the same. The diffusion for the different, even with presence of asymmetry as well as the tilt, the diffusion almost remain the same, not much change. Now we want to characterize the ratchet current in terms of various parameters of the system. So here in this plot, we are plotting the ratchet current with asymmetry, by changing the asymmetry. So versus asymmetry. So for, if you look here, although we expected that by when asymmetry increases, ratchet current also should increases, but we are not. But if you look from this graph, the ratchet current is obtaining a peak at optimal value of asymmetry. Similarly, we want to characterize by looking the ratchet current with respect to a parameter called space-dependent friction coefficient. Similarly, here also the ratchet current obtaining a peak at an optimal value of friction coefficient. And this is a velocity distribution for different value of temperature. So here, if you see here the distribution of velocity for different temperature without asymmetry. So if you look here, here is this peak, this distribution here, this show that the particle is in a potential well. This show that the particle is in the lock state. Okay, whereas these two on the negative as well as on the positive, this show the running state of the particle. That means when the particle coming out of the potential well. And here, if you look here, this is negative direction, this is positive direction. The velocity in the positive direction is more than the velocity in the negative direction, the distribution. So that's why in the plot of average velocity, we're obtaining a net positive velocity. Similarly, with including of asymmetry also, again, this is represent the lock state, and this represent the running state of the particle, and again we are obtaining the net positive velocity. Similarly, in the presence of constant tilde, even if the tilde is negative, still we are obtaining a net positive velocity. And this is a Piglet numbers, as what we have mentioned. By definition, Piglet number is the ratio of average velocity divided by diffusion coefficient, because just the particle spread also doesn't have meaning. So we also want to see the velocity as well as the coherency of the particle. So this is measured in terms of Piglet number. And if you see here in all the three values with asymmetry as well as with a small tail, it show a big value at this more or less this optimal value of temperature as what we have obtaining for peak value of average velocity at this particular temperature. So this is about the characterization of Richet effect. So in this work we study the particle dynamic in a model under the inhomogeneous periodic potential system. Also the particle current is characterized as a function of the system parameter with the inclusion of a small asymmetry as what we have seen in the result. It increases or rather it enhances the efficiency of transport. The system performance is found to be sensitively dependent on the choice of the system parameter. And due to a large parameter region, so optimizing a model with enhanced performance, which is having a direct technological application, is an open field of research. So this is the reference that I'm using. Thank you.